So hi, I welcome you all to the refreshers course conducted by Directorate of Admissions and Academic Outreach in association with Department of Sciences and Mathematics at Amrita. So as a part of refreshers course, we have a 5-day session. So we have 2 sessions of physics and 2 sessions of mathematics. And once again, I welcome you all to today's session.
Will you be able to see the screen?
Yes, sir. The screen is visible. Now it's completely fine.
Yeah. So today I'm just going to explain the basics of ray optics and optical instruments. How this, basically it is a geometrical optics, what we are going to discuss. And especially I came to know that you have some doubts in refraction at spherical surfaces and through the derivation of Lensmaker's equation. So we will just go through it slowly. And if you have any doubt, you can just ask at the end of the session. And so that's what. So let us just begin with. So first one, just to begin, let us just understand what do you mean by light. So light, it is an electromagnetic radiation and in the visible region. Actually, the wavelength is around 400 nanometer to 750 nanometer. And for most of the geometrical optics, we consider light travels in straight line with very high speed. For example, the speed is 3 into 10 raised to 8 meters per second. It is the highest attainable speed in nature that you know very well. Okay. So when you compare the wavelength of light with the objects, means even with the optical elements, what you are using, lenses and mirrors and all those things, it is very, very small. The wavelength of light is very, very small. So you can say that when it travels from one point, when light travels from one point to another point along a straight line, joining them, that is called the path. That's a ray of light. So that is called ray concept. So most of the geometrical optics, we consider the ray concept, right? I think you know that very well. But when you go for interference and diffraction and polarization and other things, we have to consider light as wave. And Huygens wave theory of light we have to consider. Okay, right. So the bundle of such rays which constitutes a beam of light. That's what you mean by light, because it is an electromagnetic wave and it is a transverse wave also. Light is a transverse wave. You know that it consists of both electric and magnetic vectors which are perpendicular to each other and perpendicular to the direction of propagation. Okay, so to move on, first, when we want to know the working of optical instruments and whatever the applications of light, we should have a clear understanding of reflection and refraction. These are the two concepts we should be very clear. So if you see, just this slide shows how a light is reflected on a mirror. Just it's a polished surface. You can take a normal mirror also. So when the light incident, it is getting reflected at a particular angle. And so you can see that the loss of reflection, for example, angle of reflection, that is the angle between reflected ray and normal to the reflecting surface or the mirror, whatever it is. So it is equal to the angle of incidence. So even if you just look microscopically, why you may have a question that why the light is reflected only at this particular angle? Why not in other angles? That question you may get. The reason is when the energy transfer takes place to the electrons of atoms present in the material, that is mirror, then how it is getting reflected back, the electrons will start oscillating so that it will, whenever a charge is getting oscillated, it will re-emit the radiation. But many electrons will radiate in different directions. Only in this particular direction, it will actually superimpose in each other and it will produce a constructive interference. So that is the reason the light is reflecting only in that particular direction. Even you can prove this by using Fermat principle. I think you are very well about Fermat. You know very well about Fermat principle. That is principle of least time. And light follows a very follows a path and that travels in a very shortest time. That's what Fermat principle states. You can prove this law of reflection using Fermat principle. Okay. So the second law states that the incident ray, reflector ray, and the normal to the reflecting surface at the point of incidence lie in the same plane. That is very, you know very well about this. So these two laws, these are the laws of reflection. One is angle of reflection is equal to the angle of incidence is equal to the angle of reflection, and the incident ray, reflector ray, and normal all are lie in the same plane. Okay, so these laws are valid at each point on any reflecting surface, whether it is plane or curved surface. Because even if you just go for concave mirrors or convex mirrors, but the law remains the same. Okay, so you have to take the point at which the light is falling, and you have to consider the normal at that point, and then it will follow the law of reflection and law of the second law, that is normal and incident ray and the reflector ray all lie in the same plane. Hope it's clear. So the the next thing is the reflection, how the reflection takes place in spherical mirrors. Okay, so normally in spherical mirror, the geometrical center of a mirror is called its pole, while that of a spherical lens is called its optical center. So in the case of lens, it is called optical center, and in the case of mirror, I will show what it is. In the case of spherical mirror, it is called pole. Okay, so the line joining the pole and the center of curvature of a spherical mirror is known as the principal axis. Okay, so whenever a line which is connecting the center of curvature, I think you know that what is center of curvature, and the pole, it is actually principal axis. So in the case of spherical lenses, the principal axis is the line joining the optic center and with its principal focus. You will see later how it is. So this is the another important thing when you want to solve the problems. Actually, I think I saw some of the questions, whether the problems are in IIT joint entrance exam level or even our Amrita entrance exam level. So it is actually, if you want to solve the problem, actually you should be very clear about the sign convention, which normally follows in school. Actually, we follow Cartesian sign convention. That is what we are following in schools for spherical mirrors and as well as lenses and whatever the geometrical optics, whatever the optical instruments we are using, and lenses and mirrors, we are using Cartesian sign convention. So what is that sign convention? So you can see it is actually a mirror. Okay, so you see that all distances are measured from pole of mirror or optical center of the lens. Optical center is the center point of this. If it is a lens, the center point is the optical center. Okay, so the distance is measured in the same direction as the incident light. Suppose a parallel beam of light which falls on this mirror. So if you measure any distances in the same direction as the incident light, then it will be taken as positive. And those measured in the opposite direction of the incident light, then that will be taken as negative. That is the first thing you have to consider. So whenever you measure a distance in the direction of the incident light, then it is positive, and you measure the distance opposite to the direction of light, incident light, it is negative. So that's what, and I hope you understand. Similarly, the heights of this object, suppose you are keeping an object, it is upwards with respect to the x-axis. So you see this x-axis, and this is, suppose if you take this first arrow as an object, so you can take this as actually positive. Okay, and then if the heights are measured downwards, it is negative. Okay, so these are the sign conventions, basic sign conventions required to understand this, to get this mirror equation and lens maker's equation, even refraction, spherical surfaces, all these things. Okay, so this is what your Cartesian sign convention. Okay, hope it's clear for you. So we will just move on to the focal length of spherical mirrors. So you can see the first diagram. parallel beam of light which falls on a concave mirror. So after reflection, it passes through a point. It is called this, that focal point. Okay, so this is a concave mirror, and so so this is focal point, and C is actually center of curvature, and this P is your pole of the mirror. Okay, so the next thing is for convex mirror, suppose if you are taking a convex mirror and the same parallel beam of light falls on this mirror, then what happens, because it is a convex, so you can see the law of reflection which still applies in all these things here. So you can just consider one ray and just take that where it is getting reflected. Okay, so it is getting reflected, and if you draw a normal at this point, then the incident angle and the reflected angle should be equal. It obeys the laws of reflection, each ray, if you consider. So that's what earlier I said, whether the surface is plane or spherical, the law of reflection still obeys. Okay, so in this case, in the concave lens, if you see, the light appears to come from this point. This is called the focal point of your convex mirror. Okay, so this is what F is the principal focus of the mirror. Okay, the next one is, if you see the other rays, apart from parallel to the optic axis, you can see the other direction also. Again, it obeys the laws of reflection. You can just see that each ray, there are two rays they have considered. So each ray, it obeys the laws of reflection. And you can see that the incident angle will be equal to the reflection angle. And these two rays will actually meet at a point. It is not at the focal point, but it is in the at some distance from the focal point. So the plane, if you consider along this, means which passes through this focal point, perpendicular to this focal point, that is called focal plane of the mirror. Okay, so whatever the object means the image of the object forms, it will be in the focal plane of this mirror. I think now you are able to understand what is focal point and what is focal plane. Okay, the plane which passes through the focal point of the mirror is called focal plane. Okay, so for other rays which are not parallel to the optic axis, it will meet somewhere in the focal plane, any point in the focal plane. Okay, that's what the idea is. Okay, hope it's clear. So the next thing is actually how this focal length F is equal to the radius of curvature divided by 2. The half of the radius of curvature is equal to focal length. So how to prove this? Okay, so in order to prove this, let us take a ray parallel to the principal axis. You just see this ray, and this CM is nothing but, it is actually the center of curvature. C is the center of curvature, and the line joining the CM is exactly perpendicular to this point, that is M on the mirror. Okay, and this theta is the angle of incidence of this incident ray, and it obeys again the law of reflection. The reflected angle also theta. Okay, and here this MD is the distance perpendicular from M on the principal axis. This is the actual perpendicular. Just we have drawn this perpendicular. So if you consider this angle MCP, this is theta. Okay, that is MCP. I think you can see this one. This is a line joining the center of curvature and this particular point. And this angle is theta, and MFP is 2 theta. Why this is 2 theta? Hope from this diagram you will be able to understand, because this is a parallel ray, and from this parallel ray to this line is theta plus theta. So it is 2 theta, and this is coming as 2 theta. Hope it is clear for you. Okay, so I will just show this. So this is the angle what we are taking, and this is also the angle. So this is just crossing. This is also parallel to this incident ray. So this is just this line is crossing this two rays, and this angle should be 2 theta. This is equal to 2 theta. Okay, so that's what here. So and tan theta. So if you take tan theta should be equal to MD divided by this CD. That is opposite side by adjacent side, and tan 2 theta should be equal to MD divided by FD. I hope you understand this actually. Okay, right. So as I said before, when you consider the wavelength, the optical size of the optical elements are much bigger. So this theta is very, very small. So since theta is small, we can just take tan theta becomes theta. Even if you could substitute the value of theta and find out the tan theta value, it is very, very small. And tan theta is equal to 2 theta. Tan 2 theta is equal to 2 theta. So if you apply this here, so MD by FD, so that should be equal to twice of this MD by CD, or you can say this FD should be equal to CD by 2. So you know what is CD? CD is nothing but the radius of curvature R. Okay, so that's what it is. And F is, you know that it is nothing but focal length of this concave mirror. So for small angles, point D is very close to point B. So since the angle is very small, this pole and this point D, the perpendicular line started from M. So this line DP is very small. So point D is very close to point B. So therefore you can write FD should be equal to F and CD should be equal to R. So this leads to the relation F is equal to R by 2. So this is why we are calling it as the focal length of a mirror is nothing but half of your radius of curvature. Okay, hope it's clear. So next is the mirror equation. How to get this mirror equation? So in order to do that, just we will try to understand how the image is formed. You know that there are two types of images. One is real image, the other one is virtual image. Okay, so the real image forms if rays actually converge to the point, and virtual image if it forms if rays appear to diverge from the point when produced backwards. Okay, so how to locate this either it is a real image or virtual image? So take any two rays, just starting from a point on the object, trace their paths and find the point of intersection, and finally you will get the image of the point due to reflection at a spherical mirror. We are going to see a schematic of that. So what are the rays we can choose? In practice, it is convenient to choose any of the following rays. Ray from the point which is parallel to the principal axis, that is you know very well, that's what we have seen, and ray passing through the center of curvature of a concave mirror or appearing to pass through it for a convex mirror. So this is a second ray you can take. And the third one, ray pass through the focus of the concave mirror or appear to pass through the focus of a convex mirror. That also you can take it. Okay, and then ray incident at any angle at the pole. Okay, so whatever the ray you consider, that means whatever we have seen, all these 3-4 rays, it should obey the law of reflection. Okay, so you should not forget that, because then only you will understand the path of the ray. Okay, so with this idea, we will just look into that. So you can see here, an object. So rays starting from the point A, and there are 3 rays we have taken. One is actually parallel to this optic axis. So you can see this is the first ray. You can just take this is the first ray, and the second ray you can just see it is pointing towards the pole of the mirror. This is the second ray, and the third ray passes through the center of curvature. Okay, so this is what the third ray. So these are the 3 rays I am going to consider. Okay, so if you just consider this ray passes through the center of curvature, then it retraces its path again. Okay, so you can see this one, this is the same path. Okay, then if you just see the other rays, so this is actually, it follows the law of reflection. So you can see this is a normal and this is the normal. This here in this case is the optic axis, this is a normal. Okay, so this is the focal point, and you can see where these rays meets, and this is a point, image point of this object point A. So this is A dash. Okay, so A dash, B dash is nothing but your image of this object AB. Okay, so it is actually an inverted image. So you can see that the distance between the focal point and the pole is the focal length, and the distance between your object and the mirror is actually your object distance U, and your image and the mirror is image distance V. Okay, so that's what it is explained here. Hope it's clear for you. Okay, then we'll move on. So this is same figure what you have seen before. So we have to find what is the relation between object distance, image distance, and focal length. Okay, so look carefully. There are two right angled triangles here. So now it is just mere mathematics. So you can just see here A dash B dash F. So this is the triangle here, A dash B dash and F. This triangle and MPF and MPF, these two triangles are similar because already you know that this P, if you draw a perpendicular from M, this point where it meets in the optic axis and P is very close. So we can just take this as a straight line. So these two triangles are similar triangles. Okay, so that's what it is mentioned here. So you can just take from similar triangles B dash A dash divided by PM. Where is PM? This PM. B dash A dash divided by PM in a similar triangle, it should be equal to B dash F divided by FP. Okay, so this is the this is possible when you have similar triangles. So B dash A dash divided by B dash F, that should be equal to sorry, B dash A dash divided by PM. This is the distance. So B dash A dash and this PM, this should be equal to B dash F, this distance and this distance. Okay, so FP. So you can still, you can just alter this B dash A dash, because here PM is equal to AB. So what you can write? You can write this one as B dash A. Just a minute. So this is BF by. So this, if you just take APB, this triangle APB, and equal to A dash, this triangle A dash PB. So these two triangles are right. That is, one triangle is with the object, the other triangle is with the image. All these two triangles are right angled triangles. So these two triangles also A dash BP, A dash B dash P, and ABP are similar triangles. So therefore, what you can write, B dash A dash divided by BA should be equal to B dash P divided by BP. Okay, so this is what you can write, another from the right angle triangles what I mentioned here. So this is another relation you can write. So you can compare these two relations. So in this case, it is B dash A. Sorry. So B dash A dash divided by BA. So because PM is nothing but BA, and B dash F divided by FP. Okay, so these are the two equations. From this you can write. So when you compare these two equations, what you will get, that is 9.4 and 9.5. So you can get B dash F divided by FP. This is equal to B dash P minus FP divided by FP. That is equal to B dash P by BP. Okay, so this is the equation when you compare. So just we have taken two sets of triangles. One is similar triangle, that is A dash B dash F and FMP. So that those are the two similar triangles, and the other two triangles are right angle triangle, that is ABP and A dash B dash P. So these are the two triangles, right angle triangles. From these two triangles, we just write a couple of equations, and we are equating and comparing those two equations, and then we are getting the relation 9.6. Okay, right. So then, so now we have to apply the sign convention. So what we have seen earlier, so we have to apply the sign convention. So you know that B dash P is actually image distance. It is measured opposite to the light traveling direction. So it should be minus, it should be negative. So minus V. And FP also, it is measured opposite to the direction. There are some hands, some doubts. So shall we clear at the end of the presentation, Lakshmi, or how it is?
Sir, we can clear it at the end of the session.
Yeah, that would be better, right? Yeah, okay. Then, so the other sign convention BP, if you take, that is also, it is opposite to the light travels. It is in the x-axis in the positive direction. So here also it is minus u. So when you substitute all these things in the previous equation, so what you obtain here, b dash f by fp, b dash p minus fp by fp, and b dash p divided by bp. So when you just substitute these values, you will get this one, minus v plus f divided by minus f. And you can just see this is equal to minus v by minus u. I'm just applying the sign convention and replacing this, the values in terms of image distance, object distance, and your focal length. Okay. So finally, I will get this mirror equation 1 by v plus 1 by u equal to 1 by f. So this is what your mirror equation. Okay. Hope it's clear for you. So once you get the mirror equation, then the next thing is, what is the linear magnification? What is the magnification? So, obviously, you know that magnification is nothing but height of the image divided by height of the object, h dash by h. Okay. So if you just take, according to sign convention, h and h dash will be taken positive or negative in order to the acceptable sign convention. So if you consider the triangles A dash, B dash, P, so this is A dash, B dash, P, and ABP, ABP, these are the two triangles, that is right angle triangles. This is triangle 1 and this is triangle 2. So these are the two triangles. So you can just write B dash A dash divided by BA. That should be equal to B dash P divided by BP. Okay. So this distance, BP is the distance between this point B of the object and the pole, and B dash P is actually distance between the image point B dash and the pole. Okay. So I have written this equation according to from the right angle triangles. So what we can do with the sign convention, this you can write like this. Okay. So M should be equal to height of the image divided by height of the object. So this comes according to sign convention. You can just see h dash by h is equal to minus of v by u. So this is what your magnification. Okay. So this is called linear magnification. Okay. So because when you go for the optical instruments, we are going to see another magnification called angular magnification. So you have to be very clear whenever we just consider the height of the image and height of the object and image distance by object distance, it is linear magnification. Okay, so proceed further. So you can just see how the image is formed with a concave mirror. So you can see this is a concave mirror, how the image formation. So the object is between the focal point and the pole. So if it is there, if you draw the axis, because you will get a virtual image. Okay, I think you know that what is the difference between real image and virtual image. So you can see that it appears the light ray appears to come from this point A dash. So this is a virtual point because this is forming a virtual image. And also the object is between F and pole. Okay, this is with the concave mirror. And then with convex mirror, again, you just consider this object. So obviously you will get a virtual image here also. So you can see this reflected ray appears to come from this point. And if you consider these two rays and just see that the reflected ray. So here also again, it follows the law of reflection. You can see that it appears to come from A dash. Okay, so if you consider these two rays and where it crosses, there only the image appears. It is a diminished, image actually. Okay. So this is the way how the image is formed by a concave mirror and convex mirror. Okay. So the next one is refraction. So let us come to the point of refraction. So it is actually when you consider refraction, light encounters two mediums. Okay. So one, maybe the simple example is one is air, the other one is glass. Okay. So that's what it means. So what you can see, the direction of propagation of oblique incident ray of light enters the other medium changes at the interface of the two media. So you can just see here, it changes at the interface. So whenever the light is incident, you can see that it is getting reflected as well as there is a refraction also. But you see, this is actually another medium. It is having something called refractive index. So you can see the Snell's law of refraction. So incident ray, refracted ray, and normal to the interface at the point of incident all lie in the same plane, that is this plane. And ratio of the sign of angle of incidence to the sign of angle of refraction is constant. That's what your refractive index of the second surface with respect to the first surface, n21. That is sine I by sine R. Okay, right. So in order to understand this refraction, whether when light goes from one medium to another medium, what actually happens? So whether the speed of light changes or the frequency changes or the wavelength changes, in order to understand that, there is a simple analogy, mechanical analog of refraction you can see here. So here you see there is a tiled concrete surface, and this is a grass surface. So you can see in the figure, and there is a drum, rolling barrel. So this is rolling in a particular direction. So you can see the direction in which it rolls. Okay, so this is the direction in which it rolls. So in this concrete surface, the speed is constant. There is no change. But once, because it is at a particular direction it rolls. So when it reaches the grass, only this part, it actually enters the grass. Definitely, you know that the grass, in the grass, when it enters, the speed will reduce. Automatically, the speed of this part will reduce. So this will be a pivot point. Then automatically it will change the direction of this barrel. Then what will happen? So it will change its direction, and also slowly all other points, the speed reduces, and as a result, it changes its direction. So you can just take this as an analogy. And at this point, I will just show an animation at this. You can just see how the refraction takes place. So hope you will be able to see this animation. You can see. Can you see the animation, Lakshmi? Whether it is.
Yes, sir. It is visible.
Yeah. So you can see the first surface is glass and the second surface is diamond. So there are two surfaces. So you can see that the light ray passes through the first surface, and you can see the second diamond, because the refractive index of diamond is slightly higher than the refractive index of first surface. You can see the refractive index of glass is 1.5 and diamond it is 2.42. So obviously the speed of light reduces in diamond. So you can just see how it progresses actually. So this is one way to understand how the refraction, how the speed of light changes when it goes from one medium to another medium, and light goes from one medium to another medium. Okay, so again, after crossing this medium, the speed of light remains the same. So this is a simple way to understand how the refraction takes place. Okay, so
sir, just give me a second. Students have started typing. It's not visible. So initially it was visible, then it got stuck, I think. So can you please play it once again?
So this is no, just a minute.
Okay, sir.
Yeah, so is it possible to see? They could see that or not?
No, sir, but it's okay. Maybe it's actually in the PPT window itself. The presentation is stuck. It's not going forward.
Just a minute. So they will be able to see now.
Yes, it's visible.
Hope it's visible. So I think now you can able to see that how it is actually the speed of light changes when it enters the glass, because the glass it is 1.5 refractive index, and diamond it is 2.42. So the speed of light in diamond is actually decreased, and when compared to the speed of light in glass. Okay, so this is just a simple way to understand how the refraction takes place. And most importantly, you know that the frequency of light doesn't change, only the speed changes. Okay, so that compensates, so that the frequency will not alter. Okay, so that's what important thing in the case of refraction. Okay, right. So I will go back to presentation again. So is it visible, the presentation?
Yes.
Yeah. So coming back to the Snell's law of refraction. So sin I by sin r is equal to n21. So n21 is nothing but refractive index of the second medium with respect to the first medium. That's what I told you. So it is a characteristic of the pair of the media what you have taken, but it is independent of the angle of incidence. Okay. And if n21 is greater than 1 or is less than I, so this is angle of refraction and angle of incidence. That is, refracted ray bends towards the normal. So that we are going to see another animation. Medium 2 is said to be optically denser than medium 1. And if n21 is less than 1, that is, or is greater than I, then in this case, it is bends away from the normal. So incident ray in a denser medium refracts into a rarer medium. So you can just see this animation. I will just share that also. 1 minute. So can you able to see that? I think
Yes,
you can see. Yeah. So you can see how this is air, this is glass. So this is the incident ray. So how this is getting, when it goes from reverse direction, denser to rarer, or rarer to denser, you can see how it bends towards the normal or away from the normal. So this is the way to understand how the refraction takes place. Okay. Hope it's clear for you, the reflection and refraction. Okay. So we'll go back to the presentation again. Okay. So the law of refraction. So you can see that N2 is the refractive index of medium 2 with respect to medium 1, and N12 is the refractive index of medium 1 with respect to medium 2. And then this is N12 is equal to 1 over N21. So this is the way you can connect it. So there are some simple results you can based on the refraction. One is a rectangular glass slab. You can see that. So the refraction takes place at two interfaces. You can see here. So, so from this, if you consider, if you just carefully look into the thing, the angle R2 of the emergent ray is equal to I1 incident ray. So this ray, emergent ray, is parallel to the incident ray, but it is shifted. There is a lateral shift. Okay. So that is because of the second refraction takes place at this point. Okay. That is when light ray goes from denser to rarer. Initially, it is rarer to denser, and then it is denser to rarer. Okay, this is one example of refraction. The another example is what is actually a tank filled with water. You can see that bottom of the tank is appear to be raised. The apparent depth is is a little bit lesser than the real depth. You can see from the top of the surface. So the apparent depth is H1 and real depth is H2. So it is divided by the refractive index of the medium. So because of the refractive index, the apparent depth is less than the real depth H2. Okay. So these are the just two examples of refraction. Okay. So now another example is the best example. You know that how the sunrise and the sunset, it appears actually due to refraction of light through the atmosphere, how it looks like. So you know that very well. So once I think if it is shared this, you can just go through it because we have to go to that refraction of spherical surface. We will go into that. Okay. So this is just another example how it takes place because of refraction. And then next is total internal reflection. So in the case of total internal reflection, you know that when light ray goes from denser to rarer. Okay. So when you change the incident angle slowly, there is refraction takes place. But at a particular angle of incidence, then what will happen is the ray, the refracted ray, which grazes on the surface of this medium, and the reflected ray and refracted ray are mutually perpendicular to each other. So the angle of incidence at that point is called the critical angle. That's what the critical angle, you know that very well. What is critical angle? The angle at which the refractor ray and the reflector ray are mutually perpendicular to each other. That's what I explained here. Actually, how this is the, one by one, when you increase the angle of incidence, I dash, first one is I dash and IC. IC is your critical angle. So you can see that how this angle, it is actually a perpendicular angle, and you can see there is no more refraction takes place at the critical angle. After the critical, if the angle of incidence is greater than the critical angle, then what will happen is there is no more refraction, only reflection takes place. That is called total internal reflection. Okay, so this is another way to explain this. Even you can explain by Snell's law of refraction. This total internal reflection can be explained. So from Snell's law, if the relative refractive index is less than 1, so that means it is not possible refractive index is less than 1, then it will be sin IC should be equal to n21. N2 is the refractive index of the second medium with respect to the first medium. Okay, so this Snell's law of, if I is greater than the critical angle, that is in this case, the Snell's law of refraction cannot be satisfied. Okay, so that's what obviously from this relation you can find out the Snell's law of refraction cannot be satisfied, and hence no refraction is possible. Okay, this is what the critical angle and total internal reflection. So there are some materials, and what is their refractive index and the corresponding critical angle is given in this table. And then you can see there are naturally you can see some of the applications of this total internal reflection. So one best example is mirage. So how this mirage happens, it is due to the total internal reflection, because during hot summer, what happens is actually the air near ground becomes hotter than air at higher levels. So when it is very hot, means it is less dense and has smaller refractive index than the cooled air. Okay, so what happens when you see the light actually appears, actually it bends, so it comes from somewhere here. Okay, so that is the reason the mirage appears. This is actually due to total internal reflection and variation of refractive index due to the temperature of the air, the layers of the air. Okay, this is your mirage. And the next one is fiber. Of course, nowadays we are using optical fibers. So how the light is communicated through optical fibers, this is also through total internal reflection. You can see in fiber, there are two things. One is core and the other one is cladding. The cladding refractive index is less than the core. So what happens is when light passes through this, it is getting total internally reflected from the cladding. So in this way, the light passes through this without any loss. So if you are just using coaxial cables, there is a loss of communication by some means. But in the case of optical light, when you communicate signals through light, then there is no loss. Even during earthquake and cyclone and all, the communication will not be disrupted. Okay, this is another application. So coming to the point, actually, what you have asked a doubt, how this refraction takes place at spherical surfaces. So let us just see quickly. So this is a spherical refracting surface. You can see that. And a point object is that this is optic axis and this is a pole. And so the refractive index, in the front of the spherical refracting surface is actually N1, and the refractive index of the spherical refracting surface is N2. Okay, so N2 is greater than N1. Okay, so what I have considered, I consider an object point O and a ray of light from the point O. It is just incident on the spherical refracting surface. So at the point N. Okay, so you know that this is actually the normal. This is starting from the center of curvature, this dotted line. This is the normal. So after refraction, because it is going from rarer to denser, it should bend towards the normal. That's what's happening here. So it bends towards the normal. And this is the image point. Okay, so this is the incident ray and this is a refracted ray. So this is incident angle, this is a refraction angle. Okay, so I have drawn a normal, means from N to this optic axis, and I consider another ray also, that is passing along the optic axis, you can see that. So this arrow, this is the second ray passing along the optic axis. So you can just see that these two rays meet at this image point. Okay, so this is your U is your object distance and B is the image distance. I hope it's clear for you. Okay, this is just simple ray diagram. Now coming to this tan of this NOM. So this is the angle. This angle is mentioned here. Tan of NOM is equal to, because the angle is small, so you can just tan theta becomes theta. So it is actually opposite side MN divided by OM. Similarly, tan of NCM, it should be MN divided by MC. So this angle, okay. And NIM, so this angle, if you take, then it is MN divided by MI. Okay, so I have just taken all these angles. Okay, so maybe you can write 1, 2, 3. So all these angles I mentioned here, 1, 2, 3. Okay, so now go to the next point. So now for NOC. Okay, so in the triangle NOC, if you just see, I is the exterior angle. So this is the exterior angle. Okay, so you can write in this triangle, I should be equal to this angle plus this angle. So I should be equal to these two angles. Okay, you can write that. So you know already what is NOM and what is NCM. So I am just substituting here in this equation 9.13. So similarly, R. So if I take R, so how to write R? So R, I can write NCM. So this angle, that is NCM, this angle, minus of NIM. So this angle. So why I am writing this? Because this angle is equal to the sum of R plus this angle. So I can write R is equal to this angle minus this angle. I can write that. Okay, so this is the second equation, and from this I am getting this. Okay, then from Snell's law, N1 sine I is equal to N2 sine R. So because it is angles are very small, so N1 I is equal to N2 R. So this is what I am getting, this equation from Snell's law of refraction. So now what I am going to do, I am going to substitute for this I and R here. So this I and this R, I am going to substitute equation 9.13 and 9.14 in this equation. I am going to substitute. So when I substitute here, you can just see in the 9, this is equation 9.14. These two equations when after substituting, so I can write N1 by OM and N2 by MI. That should be equal to N2 minus N1 by MC. So that's just mere substitution. Okay, I am not doing anything. I just substituted and rearranging. I get this equation. So this OM, MI, and MC are magnitudes of distances, and then I have to, of course, I have to apply the sign convention, which is, I said earlier. So this OM is nothing but your object distance. It is actually measured against the light propagation. So this is minus U, and MI is along the direction of actually light propagation. So it is positive, and MC also positive. This is radius of curvature. So if you apply all this sign convention here, then you will get N2 by V minus N1 by U is equal to N2 minus N1 by R. So this is the equation for spherical refracting surface. So this is the relation between object and image distance in terms of refractive index of the medium and radius of curvature of the curved surface. Okay, so this relation holds for any curved surface. Okay, so this is I have taken for one spherical refracting surface. So this could be concave or it could be convex. Both the cases it is applicable. Okay, so now I hope it's clear how the refraction takes place at spherical refracting surfaces. Now let us move on to lenses. How to derive the Lensmaker's equation. So if you see the lens in this case, so the top figure shows a thin lens. So you can see two surfaces, two spherical surfaces. One is a concave and the other one is convex. Okay, so what I am going to do to derive the Lensmaker's equation, it is very simple. So first I will consider the left surface, that is a convex surface, and only this convex surface I am going to consider, and it is similar to the spherical refracting surface what you have seen earlier. Okay, similar to this point what you have seen, okay, in this diagram. So what I am going to do, I am going to write an equation for spherical refracting surface, that is a ray of light going from rarer to denser medium. And how can I write an equation for this spherical refracting surface? Sorry. So you can get this equation N1 by OB and plus N2 by B1 and equal to N2 minus N1 by BC. Okay, so this is what the first surface equation. I am getting this equation for the first surface. Then similarly, I am considering the second surface. Okay, so I am considering the second surface and I am going to apply the same refraction at spherical surface, that is second spherical surface, and I'm going to write another equation that is minus N2 by di1, that is di1. This is after applying the sign convention, plus N1 by di equal to N2 minus N1 by dc2. So what I have done, I have written two equations, that is for two spherical refracting surfaces. One is the first surface and the other one is the second surface. So these two equations I got. Now my job is simple. What I have to do, I have actually, you can see, first case it is going from rarer to denser, and the second case it is going from denser to rare. Okay, so that's what. And also you can see the image formed by the image point formed by this first refracting surface I1 will be the object for the second refracting surface. Okay, so that is also you have to look into. So first surface, there is an image forms at I1. So this I1 will be the object point for the second surface. So final image forms at I. Okay, so this is what anyway that we are going to get from these two equations. So please remember this equation 9.17 and 9.18. Okay, now what I am going to do, so for a thin lens, BI1 is equal to DI1. What is BI1 to DI1? BI1 should be equal to DI1. So that means the distance is very, very less. So this distance should be, because it is a very thin lens. Okay, because for just writing these equations, we consider this a spherical refracting surface, but actually it is a very thin lens. So that is why I have written, so then you have to add these two equations, that is 9.17 and 9.18. You can add these two equations, and when you add these two equations, you will get an equation this N1 by OB plus N1 by D1 equal to N2 minus N1 into 1 by B1 plus 1 by DC2. Okay, so this is what the equation after adding this. So C2 is nothing but the center of curvature of this surface, second surface, and C1 is the center of curvature of this first surface, and R1 is the radius of curvature of this first surface, and R2 is the radius of curvature of the second surface. So after taking into account of all these things, you will arrive this relation. So now we have to simplify still. Suppose if you just take the object is at infinity, so you just take this object point is at infinite distance, then OB becomes infinity. So this becomes 0, and DI is nothing but your focal point. This DI is nothing but your focal point, because an infinite light rays from infinite object will focus at the focal point. So that's what I have written here. So it is F. So I'm substituting here so that I will get only N1 by F, and this becomes 0. The first one becomes 0, and this one is equal to N2 minus N1 in 1 by BC1 plus 1 by DC2. Then again, I am just substituting this sign convention for this radius of curvature. So after substituting this sign convention for the radius of curvature and the relative refractive index, so I can write the lens maker's equation, that is 1 by F is equal to N21. So how I will get N21? I'm just dividing this N1 this N2 by N1 and N1 by N1. So divide this by N1. Actually, in this case, you can just divide this N1 divided by N1. So you can write this N2 by N1 is nothing but N21, the refractive index of the second surface with respect to the first surface, and minus 1 into 1 by R1 minus 1 by R2. This is what your Lensmaker's formula. Okay, so this formula is useful to design lenses of desired focal length using surfaces of suitable radius of curvature, and this is applicable in the same way you can derive using a concave surface also. So in order to do that, you have to take a spherical concave refracting surface. You have to take into account, instead of convex refracting surface, you have to take into account of concave refracting surface. Similar way you can. Only thing, again I am telling, the important thing is here sign convention. So Cartesian sign convention you have to take into account. Okay, right. So hope it's clear. So we will see if you have any doubt at the end of the discussion. So you can see how the image formed by refraction through lenses, convex lens and concave lens. At this point, I would like to have show one animation. So I will just share that animation. I will just 1 minute. So you can just see here how when you vary actually the object point. Okay, this is the focal point. So when you vary this, how this image varies and how the size of the image varies, you can able to understand by just depending on your requirement. Actually, how do you want an enlarged image or how it is? You can just move your object actually, and this is actually you will get the equal image. You will get an equal size when your object is at 2f. Okay, that is at exactly at the center, means the radius of curvature, the point center of curvature. If you keep, then you will get exact the same size of the object. Okay, so we will go back to the presentation again. So this is how it forms through concave surface. So you can see here again I am considering 3 rays. One is parallel to the optic axis, the other one is passes through the optic center. So in the case of mirrors it is pole, and in the case of lenses it is optic center. So this is the point called optic center, and the third ray passes through the focal point. Then after passing through the lens it becomes parallel actually to the optic axis. I think this you know very well. And all these rays where it meets, you will get this. So this is exactly at okay, its center of curvature. Okay, this is distance is r. Okay, so similarly, how it is actually how it is taking place for a concave surface. Okay, that's what it takes place. How the image formation takes place with a concave surface. Okay, so in thin lens approximation, B and D are close to both optic center of the lens. So BO and D equal to minus U and DA is equal to plus V. So you can just understand this this from this previous diagram. Okay, just a minute. Okay, BO, and from this same diagram, you can understand that, and you can write the Lensmaker's equation applying the sign convention here. 1 by V minus 1 by U is equal to 1 by F. This is thin lens formula actually. Okay, so that is Lensmaker's equation. This is thin lens formula, valid for both convex as well as concave lenses and for both real and virtual images. Okay, so whenever you consider a lens, there are two foci, F and F dash. So double convex and double concave lens are equidistant. So these F and F dash are equidistant from the optical center. Okay, that you know very well. Okay, so this is regarding about your Lensmaker's equation. So you have to consider refraction through spherical refracting surfaces, first phase and the second phase, and add those two equations and just rearrange those equations and apply sign convention. You will get the Lensmaker's equation, right? Now, again coming to the point magnification. Okay, so in order to have the magnification, you know that it is actually size of the object and image. Then after applying the sign convention, you can actually minus v by u. So you can apply the sign convention and find out what is actually this magnification of the image given by formed by the lenses. Okay, so you can just simply find out from that. And then next is, what is the power of lens? So the power of lens is nothing but measure of a convergence or divergence, because you need very often that what is the power of lens. So when you go to optician, so you have your eye lenses have this much power, and you have to use some spectacles. So what is the power of lens? So it is a measure of convergence. Okay, so we will see some application in how actually it applies to your eye actually. So so when light falls on lens, it will introduce some kind of convergence or divergence for the light. Okay, so a lens of shorter focal length bends incident light more. So if you have a shorter focal length, so you can see this image. Suppose this lens is having a very shorter focal length, even if you just consider this focal length less than this point, so it bends more actually. Okay, and it converges more actually. So what happens? The power P of the lens is tangent of the angle by which it converges or diverges a beam of light falling at unit distance from the optical distance. So you can see how much the convergence, because power is nothing but a measure of convergence. So how much it converges, it is delta. So tan delta, if you take, it is h by f. Okay, f is the focal length. So tan delta is nothing but h by f. If h is equal to, suppose if you take 1, okay, this height is equal to 1. If you apply, then it is equal to 1 by f, or del is equal to 1 by f for small value of delta. Okay, for small values. So the power is nothing but, so approximately the power is nothing but 1 by f. So the power of a lens is nothing but 1 over the focal length. Okay, so the unit of power is a diopter. So 1 diopter is nothing but 1 meter to the power minus 1. So this is what the unit of your power. It's a diopter. So power of lens of focal length of 1 meter is 1 diopter, of course. So power of lens is positive for a converging lens and negative for a diverging lens. So this is where you are going to apply for your eyes, how much power it is. So suppose corrective lens of power plus 2.5 diopter. So suppose if you say, doctor saying that you have plus 2.5 diopter, then you have to use for correction a convex lens of focal length actually plus 40 centimeter. Okay, we will see that. And if you have a power of your lens, eye lens is power of minus 4 diopter, then you have to use a concave lens of focal length minus 25 centimeter. That's what your a doctor is going to just check your eye and find out what is actually the power of your eye lens. Okay, then he will suggest how to correct that. I will show you an animation for that. So we will just go for before that animation, you will see when you apply when you go for the applications of this that is optical instruments, that time we will see that. So before that, we have to just go for the combination of thin lenses in contact. Suppose you have many lenses in contact, so 2 lenses instead of 1 lens. Even if you just take your mobile camera, so if you just see the camera lenses, it is not a single lens, it consists of several lenses. Okay, so in order to get the desired magnification, so you have to take a photograph of clear magnification or clear view of that. Then you have to just find out what is the focal length of the first lens, and what is the magnification produced by the first lens, and what is the magnification produced by the second lens, and what is the total magnification. So all those things you have to take into account. Okay, so in order to do that, what we have to do, so we have to just find out what is the focal length of this actually combination. Okay, so that's what here I just mentioned here. So this is first one is the image formed by the first lens and image formed by the second lens. Okay, A and B. So there are 2 lenses, and the image formed by the first lens will be the object for the second lens, and then the image formed by the second lens will be the final image. So you can see that first lens is forming an image at I, I dash, and this I dash will be the object for the second lens B, and then second lens will form the image at the point I. Okay, so this concept will be useful for optical instruments. For example, if you need higher magnification, for example, compound microscope and telescope, you want to see a star and you want to just see, whether that two stars are very close or it is, having some distance, that is the resolving power of two stars. So you need to have a powerful telescope having high resolving power. Okay, so those cases you cannot use a single lens. So you have to use multiple lenses. Even if you come to the laboratory and see a simple compound microscope, even in the eyepiece itself, there are two lenses. Eyepiece itself, that is the lens which is closer to your eye is called eyepiece, and the lens which is closer to your object is called objective lens. Okay, so it will be combination of lenses. It's not a single lens. So that depends on your requirement. Okay, so this is what the combination of lenses, how the focal length of this two, then you can just take this, add these two equations, 1 by v minus 1 by u is equal to 1 by f1 plus 1 by f2. So the left side, it is actually the combination of, that is a thin lens equation, combination of these two equations, that is equal to the focal length of the first lens plus the focal length of the second lens. That's all, very simple. And then these are as many number of lenses as you want. You can add this actually. It is actually, just a summation of algebraic sum of the individual things. Even if you consider power this multiple lenses, it is just algebraic sum of individual powers. Okay, so this is applicable for concave lenses as well as convex lenses. Okay, so this is regarding about combination of thin lenses in contact. Okay, now we will just move on to refraction through a prism, and then you know that it is what you need actually, why you need a prism. It is just to for getting dispersion. So you can just see this triangular prism ABC. So angle of incidence, this is a particular light incident on this face, and this is actually air medium, and this is glass. So it is going from rarer to denser. Definitely it will bend towards the normal. This is the normal point, and after it bends, it just travels parallel to the base of this prism, and then it comes here, the other end, it is from denser to rarer. So this is the normal, and it is bending away from the normal. So again, the Snell's law of refraction, it obeys. Okay, and you can just see, some equations here. So what is actually angle of deviation? So how to find this angle of deviation? So you can just see this quadrilateral AQNR. This is actually the triangle. It's not triangle, it is quadrilateral angle. So two angles, that is Q and R, are at right angles. You can see this is at right angle. So you can just see here, I will just mention this here. It is at right angles here, and this is also at right angle. These two angles are at right angles. Okay, so the sum of the other angles is 180 degree. So this is 90, 90, so 180, and these two angles will be 180. So that means angle A and angle Q and R should be 180 degrees. So total 360. Okay, and from the triangle QNR, this angle, it is actually R1 plus R2 plus QNR. This should be equal to actually 180 degree here. Okay, so comparing these two equations, you can just find out R1 plus R2 is equal to A, this angle. Okay, so from these two equations, so the total deviation is the sum of the deviations at the two places. So how this deviation, total deviation, it is the deviation produced. This is the total deviation, this delta. So how much deviation is produced by this prism? This is delta. So this is nothing but the deviation produced at the two surfaces, that is I minus R1. I minus R1 is the deviation produced by the first surface. then E minus R2 produced by the second surface. This is R2. Okay, so if you just from this you can get del is equal to I plus E minus A. So this is the total deviation produced by the prism. Okay, so what is the angle of minimum deviation? I think once you come to the college, so you will first experiment, what you will do is find out the angle of minimum deviation. So in order to find the angle of minimum deviation, so you can see that there is a plot that is between angle of deviation delta and angle of incidence I. So you have to vary the angle of incidence from 0 to 80. So by rotating the prism in the spectrometer, you can just vary this I. So you can vary this I, and for each I, what you are getting actually the angle of deviation delta. From the relation, you can able to find out what is delta angle of deviation, and you are going to draw a graph. So this graph will appear like this. Okay, it is like simple parabola sort of thing. So you can see this graph, and there is a point at which the angle of deviation is minimum. Okay, that is at 40 degree, the angle of deviation is minimum. What is the speciality of this angle of minimum deviation? Okay, so the speciality is at this angle of incidence, the angle of incidence, this refractor ray will be parallel to the base. Okay, that's what it is given here. It is parallel to the base of the triangle. Okay, this is what the angle of minimum deviation. Okay, so that's what it is given. So here in this case, it is given how to find out the angle of the prism. Okay, so here the angle of minimum deviation is equal to dm, that is angle of minimum deviation in this case, because this ray is parallel to the base. So that is R1 is equal to R2. Okay, this refraction angle should be R1 is equal to R2, and this equation becomes 2R is equal to this is because this equation R1 plus R2, this is 2R is equal to A. So R is equal to A by 2. So similarly, you can write dm is equal to 2I minus A. So I is equal to A plus dm by 2. So the refractive index of the prism, you can write, it is actually from Snell's law of refraction, you can write sine A plus dm by 2 by sine A by 2. So dm is nothing but angle of minimum deviation. Okay, so this is how the refraction takes place through a prism, and how to find out the angle of the prism and then angle of minimum deviation. Okay, so there is a procedure to find the angle of minimum deviation. I think once you come to the college, when you start doing the experiment, you will find out you have to rotate, you have to change the angle of incidence by rotating the prism table, and you have to vary that, and at one particular point the image of the spectral line will stop and change in the opposite side, so that point is actually the angle of minimum deviation. So you can able to find out using monochromatic light, you can easily find out the angle of minimum deviation by rotating the prism table. Okay, you don't need to do this graph and all, you can easily find out. So the next thing is, this is the same thing, that is N21 is equal to A plus dm by 2 by A by 2. So this is actually how to find out the refractive index actually there is another prism called small angle prism, thin prism. So this angle of minimum deviation is very, very small. So in this case, it is actually A plus dm by 2 divided by A by 2. So because the angle is small, so sine A plus dm by 2 becomes A plus dm by 2 divided by sine A by 2. So this is for small angled prism. Okay. So we will, I think some hands are raised. We will see that, quickly. So this is actually how the dispersion takes place by using a prism. So if you just pass white light, it will be dispersed into 7 colors. I think the violet light will disperse more when compared to red. You know what is the reason for that? Okay. Violet light bends more when compared to red. So you should just think about what is the reason for that. What is actually the speed of violet light when compared to red light, and then connect it to bending, just relate that. Okay, and then you can just see some applications of natural phenomena due to sunlight. You can able to understand the rainbow and how this rainbow appears, when sunlight passes through the raindrops, how the rainbow appears. Actually, this is because of dispersion, and there are phenomena takes place: dispersion, diffraction, and reflection. by spherical water droplets. You can see that in the diagram, how the rainbow appears. Okay. Similarly, there are other things also. Scattering of light. There is something called Rayleigh scattering and Raman scattering. There are two types of scattering. Only, I think, at your level, only Rayleigh scattering is important. So you can just, this is Rayleigh scattering. It is inversely proportional to the fourth power of the wavelength. So that's what your Rayleigh scattering. Okay, so light of shorter wavelengths is scattered much more than light of longer wavelength. That's what you have seen before. Okay, in the case of dispersion, but here also scattering also, the light of shorter wavelengths is scattered more when compared to longer wavelength. Okay, so that is the reason the bluish color, the predominance in the clear sky. So why the sky appears blue? Because the blue light scatters more when compared to red light. And similarly, but in the case of sunset or sunrise, the sky appears reddish. So there also, that is because of scattering. So you know why it is actually. Okay. So the other phenomenon is there are two types of rainbow. One is primary rainbow and the second one is secondary rainbow. So you just see the primary rainbow. So that is actually how it appears here. Red light from drop 1 and violet light from drop 2 reaches the observer's eye. So there are two drops. The light refraction, refracted right through these two drops, you can just see. So violet from drop 1 and red light from drop 2 are directed at level above or below the observer. You can just see here. This is the observer point here. So you just see what is the angle at which the violet light reaches your eye and the red light reaches your eye. And so here again, the primary rainbow is a result of three-step process, that is refraction, reflection, and what is the other one? Scattering. Okay, it is not again refraction, it is scattering. Okay, next one is a secondary rainbow. So this is you can just see what is secondary rainbow. So this is actually two internal reflections inside the raindrop. So you can see here, instead of one reflection, so you can see two reflections here. So first here and the second here. So I hope you can able to see. This is the first reflection and this is the second reflection. So this is for red light, and you can see this is sunlight incident, and it appears here and it comes out. And this is also here the other drop. So because of this, you are getting the secondary rainbow. Okay, these are the two rainbows. For primary and secondary rainbow, it is just applications of this scattering, refraction, and reflection. And then the other one is we are coming to the optical instruments. So there are several optical instruments. So the best thing is, first one is we will start from eye. So we'll directly go to the eye actually. So you can see here, eye, this is a lens actually. Okay. So light actually falls on this lens, and this focal length, this size of this pupil, this is actually the pupil actually. It can change under the control of these muscles actually. Okay. So the focusing can be controlled by these muscles, and the image of the object will be formed on the retina. Okay, this is the retina, and there is optic nerves, and from it will send to your brain, and you can able to see what you are looking. Okay, so this is what the normal eye actually. And then if you just see, as I told you, what is actually the problem with your eye. Suppose you are not able to see. Usually, the minimum distance at which you can able to see a clear image is least distance of distinct vision actually, or near point. It is 25 centimeter actually. So this is represented by the symbol D. Okay, so this D is the normal for normal person. So this D changes with the age. Okay, so because this mirror means this muscles, it is actually, it loses its effectiveness when it is when you are getting old. So what happens is the flexibility will not be there. So the near point may be close as about 7 to 8 centimeter in a child of 10 years of age, because that time also it is it may not have that much flexibility, and may increase to as much as 200 centimeter at your 60 years of age. Okay, so if an elderly person, if he tries to read the book at about 20 centimeter, it will appear blurred. Okay, so the reason is because it is not focusing, that is your eye lens is not focusing the image exactly at the retina. Okay, so that's what happens in the first image. So it focuses somewhere before the retina. Okay, so that is why you will not be able to see the image clearly. So there is this thing for, I will just show that. So you can just see here how this because it is focused away from the retina. So by using a convex lens, I am bringing the focus to the retina, something like this. So hope you understand. So in addition to this eye lens, I am using some external lens. That's what the eye doctors will do, opticians will do. And they will put a concave, depending on the power of your lens, eye lens. They will use either a concave lens or a convex lens to correct your focal point of your eye lens. Okay, so that's what normally they do in the. Okay, so this is by using a concave lens. You can just bring back to that. Similarly, this is again the same thing. There are different names you can, myopia and nearsightedness, farsightedness, all those things. So this is all because of this problem with your eye lenses, actually, because of you are getting old, or sometimes you are just too much of computer. If you see, you have to, your muscles will lose your means the flexibility, then you have to go for a spectacle. Okay, there is no other way. Okay, right. So this is your eye, and here there is another problem with your eye is actually astigmatism. Astigmatism is also when the cornea is not in spherical shape. Okay, so if this is not in spherical shape, then what will happen is, if you are just looking at a wire mesh, it will appear like this. Okay, so because the reason is your cornea, that is it is not spherical, it's a defect in eye lens, it is not in spherical shape. Okay, so how to correct that? In order to correct that, even I think you might have heard that your eye has some astigmatism, so you have to use some cylindrical lens. So if you are using some cylindrical lens, then you can able to correct this astigmatism. Okay, so this effect also can occur along with myopia and hypermetropia. So you can just see these things are not related to this optical things. So this eye lens, this nearsightedness and farsightedness only, it is related to your optics, that is ray optics. Okay. Next is a microscope. This is actually a simple microscope. Actually, it's a magnifier. I think whenever you go and read your palm, astrologer to read your palm, they will use a magnifying lens. Okay, so that is actually because your eye, if you just want to higher magnification, you cannot bring your hand beyond your near point. Okay, so if you bring anything close to your eye, it will be blurred. You cannot get the clarity beyond your near point. So what you have to do, you have to enhance your you have to magnify, you have to increase the magnification of your object. So you have to go for a lens. Okay, so that's what here so this is your eye. So this is the second figure. If you just could see that, this is the angle subtended by the image of height h at your eye. Okay, so this is at 25 centimeter. So if you want to bring closer so that you will get better image, magnified image, so what you have to do, you have to put a lens. Just look into the first image in front of your eye, so that you can just bring close this object, the same object at 25 centimeter distance, you can bring it closer. Okay, so now it is very close to the focal point of your lens, focal point of your lens, so that it will form the refractor ray will pass through these lenses, and when you look through this lens, the image, enlarged virtual image, will form at infinite distance, means at longer distance. So that's what the simple magnifier does. Okay, so you can just see here exactly at a focal point. This is actually away from the focal point, the first figure, and the last figure is exactly at focal point. So the eye focuses at infinite distance. Okay, so this is what regarding your simple magnifier. So similarly, the magnification also you can find out. This is actually linear magnification. It is again V by U. So you know that V into 1 by U. So 1 by U you can find out from lens means thin lens equation. It is equal to 1 by V minus 1 by F. So you can just simplify this. It is equal to 1 minus V by F. And this magnification is nothing but 1 plus D by F, because V is nothing but D. D is the near point. So it is 25 centimeter. It is 1 plus 25 by F. F is the focal length of the lens actually. Okay, so this is what your magnification of this simple microscope. Okay, simple magnifying glass. Okay, so this is actually another thing with the simple magnifier is actually that's called angular magnification. So angular magnification is nothing but, you can just see here. I will tell you in a simple way in this diagram. So the angle subtended by the object at your eye without any lens, okay, that is theta naught, and the angle subtended by the object at your eye with the aid of this lens, this is theta I. So theta I by theta naught will give you angular magnification. So the linear magnification is h dash by h or minus b by u, but the angular magnification is, it is theta I by theta naught, the angle subtended by the object at your eye without any lens, with lens divided by without any lens, that is theta I divided by theta naught. That is what your angular magnification. That's what explained here. So how to find out theta naught? Okay, the angle subtended. Tan theta naught is equal to h by d. Because of small angle, it is theta naught. Theta naught is equal to h by d. H is the height of the object and d is the near point. Okay, so this is actually another relation from your linear magnification that you know very well. So from this, what you can do is, so this is again tan theta, this angle subtended by the image. So that's what I said, it is theta. Theta instead of theta I have to, here it is mentioned theta. So angle subtended by the object without any lens is theta naught. So theta by theta I by theta naught again. So that's what the angle subtended by the object. It is theta I is equal to h by f, and theta naught you know already from the previous page. So from these two things you can find out what is the angular magnification d by f. Okay, so there are two magnifications. One is linear magnification, the other one is angular magnification. So with this idea, we will go for compound microscope. Okay, so I think it is time. I think Lakshmi, shall we stop at this point?
Yes, sir. We can stop at this point.
Yeah, because there are two more things. One is compound microscope and another one is telescope. So I think these two things only applications. I think they can just go through.
Read those topics. Yeah. Actually, the two topics that students have opted for are already covered. So students, maybe if you have any questions, you can type in the chat box. We'll have a 5 minutes for this Q&A part. So you can stop sharing your slides.
Yeah, I will stop it, right?
Yeah, you can stop sharing the slides.
Just a minute.
So I feel like this was a whole revision. This was a revision for the whole chapter optics.
Yeah.
And I think one student has asked one question. So sir, I'll just read out the question.
Yeah, I could also able to see that.
Okay.
So from first one, I think.
Yeah,
so you can read. Yeah,
related to Snell's law. Yeah. So by Snell's law, we know that if a light ray goes into a medium, its velocity decreases. But what is the scientific reason why the velocity is decreasing? Is it because of the atoms of the medium that reduces the velocity of the light? So he just want to have an idea about why this is decreasing.
Okay, exactly. Because when the medium consists of, the optical density is, that actually the equation for refractive index, actually, n is equal to c by v. That is the velocity of light in vacuum divided by the velocity of light in the medium. Actually, the velocity of light in the medium decreases because of the optical density increases. Okay, so it reduces the speed of the light when it moves through the denser medium. So that is the reason. Okay, so always, and you can just see that the refractive index should be greater than 1 actually, because it cannot be less than 1. If it is less than 1 means the velocity of light in the medium should be greater than the velocity of light. That is not possible actually. So so the refractive index, which can give you an insight into this, why the speed of light decreases inside the medium, denser medium actually. As you said, it is because the speed of the light is obstructed by the constituents of the medium.
Okay. So, sir, we have one more question.
Yeah.
So it's like the focal length of plane mirror is infinite. So what is the focal length of a glass slab?
Glass slab, because see, it doesn't converge or diverge the light, right? So you cannot, it doesn't form any image actually, image of your, so either for to get the image, either the light ray should converge or it should diverge actually, so that you can get the image point. So I think that's what the answer for your question.
Okay, sir. Actually, students have started asking questions related to simple and compound microscope also. So it's like all the, can you just explain by comparing the formulas by comparing both simple and compound microscope? If it's, yeah.
So shall I go back to the presentation again, or?
Yeah, maybe we can just wind up in 2 minutes. You can present it, I think.
Yeah, 1 minute.
I can see 2 questions related to this topic, so that's why.
Yeah, one. Doesn't matter. So you can able to see that, right?
Yes, sir. Yes, sir.
Yeah. Okay. So this is what the first we'll take the compound microscope. You can see this is actually the ray diagram of a compound microscope. So this is a combination of lenses, as I said before. So you have a lens which is of shorter focal length and which is objective, which is near to the object, and this is another lens which is near to eye. So this is eyepiece. Okay. So as I said before, whenever you have a combination of lenses, the image formed by the first lens will be the object for the second lens. Okay. So in this case, if you could see, the image is at point B, and it will object is at AB is at a point B actually here. So you could see that the image is at A dash B dash. So this will be the object for the second lens, eyepiece. Okay. So this is exactly at the focal point. So you can see that it forms an image at infinite distance. Okay. So this is what, because you need magnification, that is your objective. So this forms the magnification of the image, using the combination of lenses. So only thing is you have to find out the magnification of the eyepiece and the magnification of the objective, and then what is the total magnification. Okay, the total magnification is nothing but magnification of the objective multiplied by the magnification of the eyepiece. Then it will give you what is actually the total magnification. And you can see here, the focal length of the eyepiece is very short, shorter than the focal length of the eye lens. So you can see that. And also there is a distance between this focal point, second focal point of your objective, and the first focal point of your eye lens. There is a distance that is called tube length. Okay, so that is also there in the compound microscope. So so we will just move on to this actually. First, we have to find out what is the linear magnification due to objective. So the objective and the object is placed near the objective. It is not at infinite distance. So we have to find out what is the linear magnification produced by the objective first. So that's what given here, h dash by h. So m naught is equal to h dash by h. It is nothing but L by f naught. What is L? L is nothing but your the distance, your image distance. So that's what given, and this is actually f naught is your focal length, h is your focal length. So you can just find out tan beta. So where is beta here? This beta, tan beta is equal to what is your h by f naught. So h is your height of this image, has h by f naught. So this is f naught is this h. This is h. So this point also h. So you can just see here. So this point is h actually, and this is beta. So tan beta is equal to h by f naught. So f naught is the focal length of the objective, and then what you have to do is that is nothing but h dash by L. Okay, so this is what your tan beta. H dash is the size of the first image. H dash is the size of the first image. Okay, and object size being h and f naught being the focal length of the objective. Okay, so first image is formed near the focal point of the eyepiece. That's what important here. So the first image is formed near the focal point of your eyepiece. Okay, so distance L, that is the distance between second focal point of the objective and first focal point of the eyepiece, is called the tube length. That's what I told the tube. What is tube length? Tube length. It is approximately equal to the focal length. No, it's not approximately equal to. This is actually tube length actually. Then from this you can find out what is the angular magnification of the eyepiece, because for objective you have to find the linear magnification, and for eyepiece you have to find the angular magnification. You know the relation for angular magnification, M is equal to 1 plus d by fe. D is nothing but near point. So this angular magnification is actually it is approximately equal to, because the final image is formed at infinity, so it is due to eyepiece is d by fe. Okay, so now what is the total magnification? As I told before, so linear angular magnification multiplied by linear magnification, L by f naught into d by fe. This is the total magnification of your microscope. Okay, so this is what achieved. So depending on your focal length of the objective and eyepiece, your magnification will vary. Okay, so you know that here it is difficult to make focal length of much smaller than 1 centimeter. Also, large lenses are required to make L large. Okay, so you should have a better limited magnification by using combo. There are 2-3 microscope, optical microscope, by using light. So that if that magnification is not sufficient, suppose you want to see more details, then you have to go for then the next microscope, that is scanning electron microscope. Okay, something like that. So scanning electron microscope, you have to use the waves associated with the electrons, that is de Broglie waves. So that will give you better magnification. When you are using Rayleigh criterion and all, so you need to increase the resolution of resolution is directly connected to the wavelength of light. So when you consider the de Broglie wavelength, it is very, very small when compared to normal wavelength. So you can use waves associated with the electrons to get a better magnification. So that depends on your requirement, what you want to see. Okay, this is regarding your compound microscope. Then next is refraction type telescopes. Okay, so in the case of refraction type telescope, in both the cases you will have angular magnification of distant objects, because when you are looking through to stars and all, okay, you have to get a better I think you might have seen there are different huge telescope, Hubble telescope for example. Okay, because you have to see the distances, the stars at very long distances. So what you have to do, you have to have a very big lenses, but normally refracting type telescopes are not useful very much. So because it will give you chromatic aberration and other sort of aberrations with the lenses. So you have to go for reflecting type telescopes. I think the mirror itself, it is a few hundred meters. I think you can just check in the web, and you can find out. They will clean by standing on the mirror. They will clean the telescope mirrors. Okay, so like that mirrors they will use. So here the magnifying power is the angle beta subtended at I by the final image to the angle alpha which the object subtends at the lens or the eye. So M is equal to beta by alpha. Okay, so it is H by Fe into F naught by H. So this is nothing but the simple relation for refraction type telescopes. F naught focal length of the objective divided by focal length of the eyepiece. Okay, so and the length of the telescope tube is F naught plus F. Okay, so it can be useful for both terrestrial and astronomical observations, but there are some difficulties with this. And this is what your telescope. So here you see the second focal point of your objective is exactly coinciding with the first focal point, your eyepiece. Okay, and the rays from object at infinite distances will form an image at the focal point, and this will be the object for the eyepiece. Okay, so that the image will form at infinite distance. Okay, so that you can able to see the stars. This is the ray diagram for your actually telescope. So here there is no tube length and all. It is exactly F naught and Fe are exactly that matches, means the point is matching, but the focal length of the eye lens is very less compared to the focal length of the objective, exactly opposite to the compound microscope. And so you can just see that the advantages of reflecting telescopes: no chromatic or spherical aberration, and mechanical support also less problem, because the alignment also problem in the case of lenses. So usually people prefers reflecting type telescopes. Okay, so even you can able to see when you come to Amrita, there is a telescope you can able to see through through the telescope you can visit, you can see the stars and all. It's a refracting type telescope. Okay, but reflecting type telescopes, you need a huge mirror, a concave mirror is required. So to get the reflecting light reflected from the point. So here is a simple example of reflecting type telescope. So you can see here, after reflection, actually it has to go through this one, the point through this tube. So there is a secondary mirror actually people will use, so that the loss of light, because if you are not using this secondary mirror, so only a small portion of this light will pass through this eyepiece. So in order to avoid that, we can use a secondary mirror, so that after reflection from the secondary mirror, the light will pass through this eyepiece. Okay, so most of the light will pass through the eyepiece. So this is what reflecting telescopes, and the magnification of reflecting type telescope is refracting telescope is F naught divided by Fe. That's what we have seen, I think. Yes.
So I think students have a clear idea about these topics also now.
Hope I think it's clear.
Yes, yes. So it's like students have now received a time where their whole chapter revision is now complete. So
yeah,
we are really
I saw one question actually. What is chromatic aberration and spherical aberration? Actually, chromatic aberration is nothing but it is related to the colors. Chrome is nothing but color. So when you see, you know that a lens is consists of small prisms actually. So the focal point for violet ray will be different than the focal point of the red ray. Okay, so the violet ray and red ray will focus at different points. So the image will not be at a single point, it will be lengthened. So that is called chromatic aberration. Spherical aberration is nothing but different sections of this lens will form the focus at different points. So that is called spherical aberration. So chromatic aberration will form with white light, and spherical aberration will form with even monochromatic light. Okay, that's what the aberrations actually.
So I hope the session was really wonderful, and all of you have received a lot of information. So thank you so much, students, for attending this session. So we'll have one topic about mathematics tomorrow.